Alright, welcome back everyone. This is lab number 7 for Math 155. Today we will be talking about implicit differentiation and implicit plots. By now you should have learned what implicit differentiation is in your lecture. We use implicit differentiation when we have an equation or a function of two variables, namely x and y. In Calculus 1, at least at Lehman, we do differentiation in single variables, meaning just in terms of just an x or just a y. However, sometimes we need to use or we need to take the derivative of an equation or a function that has two variables. And to do this, we use this method called implicit differentiation. You will see why this method works in a multivariable class like Calculus 3. There you will actually view a proof of this particular result and how this is just a special case of something that will come later. Today I will do one example, and this particular example will help you solve all the questions in your lab. So without further ado, we're considering the following equation: y squared plus x squared equals 9. We know from college algebra, for any college algebra course, that this is simply the equation of a circle. I want to plot this equation using the new command that I will teach you today called implicit plot. And then when plotting, we will be using the parameter called a scaling equal constraint. I want you to describe the shape of the graph, find the tangent line at a particular point, and then plot the tangent lines with the graph together on the same picture. Notice that there's a hint there. There will be, at least for this problem, there will be two tangent lines. So without further ado, let's get into this. So the first thing that we will do is open a new package. And the reason for that is because the implicit plot command is contained in the package called plots. And before we could use that package, we have to tell Maple that we want to use that package so that Maple could load it. So we're going to use the command with, and then with parentheses, plots. This will make sure that we are opening up the particular package. So once we do this, you will notice that a bunch of commands appear in blue. So we could actually now use any of these commands, but the one that we're interested in is implicit plot. Notice that you could also plot in 3D. You could do an implicit plot in 3D. To use the implicit plot command, we simply type it implicit plot, parentheses. Then we type in our equation. So it's y squared plus x squared equals 9. And my parameters are going to be, well, I'm going to say x equals negative 10 to 10. That's my scale for the x-axis. Y equals negative 10 to 10 as well. And scaling equals constraint. When I press enter, I should have the equation of a circle. And lo and behold, I do. I have an equation of a circle with radius 3. Now that I have my picture, I have to find the equation of the tangent line when x equals 1. Well, if you notice, when x equals 1, if we were to draw a vertical line here, we will hit the picture in two different points, up here and down here. That tells you two things. Number one, that this is not a function, which we know. And number two, that we will have two tangent lines when we start looking for it. Now, to find the tangent lines, we first need to find the slope of these tangent lines, right? That's the first thing that we do. But to find the slope of the tangent lines, we need to take the derivative of this equation. And as you can see, this is an equation in two variables. So we in the past learned two methods of taking the derivative. I taught you the diff command, which takes the derivative in terms of one variable. So if I was to do this, if I was to use this command, I would use y squared plus x squared equals 9, and then I'm taking the derivative with respect to x here, and I get that 2x equals 0, which is not what I'm looking for, because if you remember from your class, when we take the derivative implicitly, we should get that dy dx or y prime equals something in terms of x and y. So this doesn't do it for us. If we use the other command that we learned in class, capital D, to take the derivative, then when I plug in y squared plus x squared equals 9, now I get that 2 dx times x plus 2 dy times y equals 0, which is what we're looking for. Now we have this in terms of dy dx. Now we have to solve for dy dx. So I'm going to use a solve command. So solve, and I'm going to use, again, the percentage symbol. From a previous lab, I told you that the percentage symbol simply takes your last result and plugs it in your next command. So this is going to take the result number 3 and plug it in. And I'm going to be solving this for capital dy or dy dx. When I press enter, I should get what this is equal to. Notice that that is equal to negative dx times x over y. Dx times x is just the derivative of x. Well, what is the derivative of x? The derivative of x is simply 1. So what I have really is negative x over y. So what I have is that dy dx equals negative x over y, which is correct. This is what we're looking for when we are talking about implicit differentiation. But notice that this took me 2 steps to do. On Maple, we actually have one command that takes care of implicit differentiation for us. Before I use that command, however, I'm going to define f to be the following. F is going to be our equation, y squared plus x squared equals 9. Now I'm ready to use my implicit differentiation command. The implicit differentiation command in Maple is simply implicit. So implicit diff, D-I-F-F. So implicit diff, parentheses, and now I'm going to put in my new variable f, which contains my equation, and then the parameters of my equation, or the variables, which are y and x. If you had different variables, like let's say r and t, then instead of putting x and y, you'll put r and t. When I press enter now, I get that the derivative implicitly of this equation is negative x over y, exactly what I had up here. This only takes 1 step, whereas this takes 2 steps. Yes, you may say I define f up here, but I didn't have to do that. I could have just simply put in y squared plus x squared equals 9 here, comma x, comma y, comma x, or xy, and I would have still gotten the same result. Okay, so now I have what the derivative is. The derivative of my equation is negative x over y. However, to find the slope, I need a value for x and I need a value for y. Here I only have one value for x, namely x equals 1. So I need to find the values for y when x equals 1. So to do that, we're going to use another solve command. So I'm going to do solve, and I'm going to do y squared plus 1 squared, which obviously we know that that's 1, equals 9. And I'm going to solve this for y. This is basically solving our original equation to find or locate the point up here and the point down here. So when I press enter, I'm going to get the value for those 2 points. So I get that one of the values is 2 times the square root of 2, and the other value is negative 2 times the square root of 2. And that makes sense, because if we notice here, this point is in the first quadrant, which means that it's a positive number for y. And this point right here is in the fourth quadrant, which means that it's a negative number for y, which basically means that our numbers are in fact correct. Now we need to actually find both lines. So you could use the point-intercept form of the line, y equals mx plus b, or you could use the slope y-intercept. The slope point formula form of the line, which is y minus y1 equals m times x minus x1. So you can use either or. I'm going to use y equals mx plus b because I just think it will be easier. So I'm going to use another solve command, and I'm going to pick the point. Well, before I do the solve command, actually, let's find the slope because I'm going to need the slope m for either one. So let's actually find the slope. So I'm going to call the first slope m1 is going to be the slope that I get when I plug in 1 and 2 times the square root of 2. So that means that I have minus 1 divided by 2 times the square root of 2. And I get negative square root of 2 over 4. My second slope, which I'm going to call m2, is going to be minus 1 again, but in this time it's going to be divided by negative 2 times square root of 2. And that's going to be positive square root of 2 over 4. So now I'm ready to use my solve command. So I'm going to use solve. And now that I have the slope for this particular line, so I'm actually going to use the points that I have here. I have the point 1, 2, square root of 2, and 1, negative 2, square root of 2. So I'm going to use those points. So that means that for my y value, I have 2 times the square root of 2 equals, well, m1, which is my first slope, times, what is the value for x here? Well, the value for x is 1, plus b, and I'm solving this equation for b. So now I have that my y-intercept, when I do this, is 9 times the square root of 2 over 4. So I have that the y-intercept of the line is 9 times square root of 2 over 4. So my line really is, my first line, my first tangent line, I'm going to call it L1, is going to be the following. It's going to be y equals m1, because I use the first slope, times x plus this result here, which is 9 times square root of 2 divided by 4. Okay, so this is my first tangent line. My second line, L2, is going to be very similar actually. So I'm going to do solve to solve for the second line. So I'm going to use solve, and I'm going to use the second point. So I'm going to use 1 and minus 2 radical 2. So I'm going to have negative 2 times square root of 2 equals, well, now I have m2, which is my second slope, times x. Well, x was still 1, plus b, and I'm solving this for b. So I get that the second value for the y-intercept is negative 9 radical 2 divided by 4. So that means that my second tangent line is going to be L2 equals, colon equals, y equals, well, my second slope, which is, I name m2, times x, and then minus 9 times the square root of 2 divided by 4. So that is my second line. Now notice that I use the 2 points that I found. I use 1 and 2 radical 2 and 1 and minus 2 radical 2. That is because I know that my line is going to go through those points. It has to go through those points. Okay? So now to plot both of these lines with the original equation all on the same picture, we are once again using implicit plot. So once again we'll use implicit plot. But now to graph, we will use square brackets to put all three equations on the same graph. Now, when we use a regular plot, we use squarely brackets. Keep that in mind. For implicit plot, we're using square brackets. So I'm going to use implicit plot, my original equation, which was y squared plus x squared equals 9, comma, what I have up here for y, which is y equals, and it's important. It is important that you put the y equals because we're using this implicitly, so we need both variables. And y equals this for L2. And this is all separated by commas. Then we're going to close the square bracket, and we're going to put another comma so that we can put our parameters. So x equals minus 10 to 10 again. Y also equals minus 10 to 10. I'm going to opt to not put in the scaling constraint right now. When I press enter, I should have all three images on the same graph. And lo and behold, I do. I have my circle, which, because this picture is not constrained, it looks like an oval. And then I have my two tangent lines going through them. Now, I went through all the work of actually defining my tangent lines as L1, L2, and my circle as F. So I could have just used those variables as well. I could have done implicit plot F, comma, L1, square brackets, F, comma, L1, comma, L2, comma, after the bracket, so I could put my constraints, x equals negative 10, well, negative 10 to 10, comma, y equals negative 10 to 10, and finally, scaling equals constraint. Oops. Make sure that you put your equations correct. I put LQ instead of L1. And there we go. So we have, now we could see a circle. That's what the scaling constraint makes sure that the picture doesn't get changed by our scales. So now we have a circle instead of an oval, and we still see the tangent lines going through this particular points. For your actual lab, this is what you have to do, all these steps. So you only have to do the with plot step once. You don't have to do it multiple times. Once you do it in the first part of the problem, you don't have to do this again for all the other problems. This is going to work for your entire worksheet. And there are other packages that Maple has. It's not the only one. And if you want to continue to use Maple for research, or for projects for other classes, or even to program, if you want to go into the computer science route, I highly suggest that you start looking at the packages that come with Maple and the programming that we could do using Maple. Finally, we get ready to save our work, and again, save as a PDF file. So, as I've shown you before, you're just going to click on print, change that to save as PDF, and then save your work as a PDF file. Thank you for your attention.